Something is sitting at the center of our galaxy. It has been there for billions of years. It bends stars around it, like water around a drain. It warps light, distorts gas clouds, and forces entire stellar systems into orbits so tight and so fast that the stars move at a measurable fraction of the speed of light. For decades, the explanation seemed settled: a supermassive black hole. 4.3 million times the mass of the Sun, compressed into a region smaller than the orbit of Venus. The consensus was firm enough that in 2020, 2 astronomers shared a Nobel Prize for measuring it. And yet, the official Nobel citation is careful with its language. It does not say black hole. It says a supermassive compact object at the center of our galaxy. That distinction matters more than most people realize. In 2022, the Event Horizon Telescope released an image that spread across every major publication on Earth. Glowing gas, twisted into a ring by extreme gravity. A dark center surrounded by light. It was described everywhere as the first direct image of our black hole's shadow. But here is what that image actually shows. Hot matter circling something, bent into a ring by something, casting a shadow against surrounding gas because of something. What that something actually is, that question, it turns out, is still open. A paper published in February 2026 in the monthly notices of the Royal Astronomical Society is asking that question seriously. Researchers at the Institute of Astrophysics La Plata in Buenos Aires ran a detailed statistical comparison between the standard black hole model and an alternative, a dense core of dark matter at the center of the Milky Way. They tested it against the orbital data of the closest known stars to Sagittarius, including a star called S2, which completes a full orbit every 16 years, moving at roughly 8% the speed of light at its closest approach. The result of that comparison produced a number that is difficult to dismiss. Less than 1% difference. A dark matter core, under the right conditions, produces the same gravitational effects on those stars as a black hole does. The orbital paths are indistinguishable within current measurement precision, and the image from the Event Horizon Telescope, that ring of light, that central shadow, it appears the dark matter model can reproduce that too, because the gravity of the proposed dark matter core would bend light with nearly identical force. The data we currently have cannot tell the difference between the two. That is not a claim that the black hole is wrong. The consensus remains, but it is a claim that something else fits the evidence. Something that, if true, would not just reframe what sits at the center of our galaxy. It would answer one of the deepest unresolved questions in all of physics. Because the object proposed to replace the black hole is not just a compact mass. It is a clue about what dark matter is made of. And dark matter makes up roughly 85% of all the matter in the universe. To understand what the La Plata team is actually proposing, it helps to start with what we do not know. We do not know how supermassive black holes form. This is not a minor gap. Stellar black holes, the kind that form when a massive star exhausts its fuel and collapses, are well understood. The physics is mapped. The signatures are observed. Astronomers estimate there may be close to 1 billion of them, scattered through the Milky Way alone, but Sagittarius A sits in an entirely different category. At 4.3 million solar masses, it is too large to have formed from any known stellar collapse. There are no stars massive enough to produce a black hole of that scale, and intermediate pathways, chains of mergers, rapid accretion in the early universe, remain theoretical. The mechanisms are proposed but not confirmed. So when researchers defend the black hole model, they are defending the best available explanation for an observed gravitational effect, not a directly observed object. Black holes do not emit light. They do not have surfaces that reflect anything. Their existence is always inferred from what happens around them. The orbits of nearby stars, the behavior of surrounding gas, the distortion of light passing close to their edge. This is what leaves the door open. The idea that Sagittarius A might not be a black hole has never fully disappeared from the scientific literature. Over the decades, as the S-star data accumulated and some alternatives were ruled out, the debate moved to the margins. But it never ended. Boson star models remained, gravistar models remained, and a third class of proposal, compact cores made entirely of dark matter, persisted quietly in the background. What the 2026 paper did was take one of those quiet proposals and test it with precision. The dark matter candidate at the center of this model is called a dark fermion. The idea was first put forward in 1969 by astrophysicists Ruffini and Bonazzola, and it has been revisited and developed steadily since. Dark fermions are proposed as elementary particles, subatomic in scale, invisible to every detector currently built, interacting with the rest of the universe through gravity, and nothing else. What makes them different from other dark matter candidates is a property inherited from quantum mechanics. Fermions, the class of particles that includes electrons and quarks, obey what is called the Pauli exclusion principle. No two identical fermions can occupy the same quantum state at the same time. They cannot overlap. They resist being compressed into the same location. This is the same principle that keeps electrons in their shells around atomic nuclei. It is why matter has structure. It is why solid objects do not pass through each other. Dark fermions, if they exist, would carry this same resistance. Under the right conditions, dark fermions could gather together in enormous quantities. Gravity would draw them inward, but the exclusion principle would push back against collapse. The result, according to the model, would be an ultra-dense, stable sphere. Not a singularity, not an object with an event horizon. A compact body held in equilibrium between gravitational pressure pulling in and quantum pressure pushing out, and at sufficient mass. This object would generate gravitational effects essentially identical to those produced by a supermassive black hole. The stars orbiting it would trace the same paths. The gas swirling around it would behave the same way. The light bending around it would form the same ring. The central shadow would appear. From the outside, with the instruments currently available to us, it would look exactly like what we already see. The difference would be internal and invisible. A black hole has a point of no return. Cross the event horizon and nothing comes back, not even light. A dark matter core has no such boundary. It is dense, extreme, gravitationally intense, but it has a surface in a sense, rather than an abyss. Photons that approach it closely are bent severely, but they are not trapped. They curve and escape. This distinction, invisible to current telescopes, is not just a technical detail. It is the hinge on which the entire question turns. There is a structure to this proposal that goes beyond Sagittarius A itself. Most alternative models for the galactic center treat the compact object and the dark matter surrounding the galaxy as two separate things. The black hole sits at the center. The dark matter halo extends outward in a diffuse cloud, stretching far beyond the visible disk of stars and gas. Two distinct structures, two distinct problems, related only by coincidence of location. The fermionic dark matter model does something no other hypothesis attempts. It connects them. The proposal from the La Plata group is that the dense core at the center of the Milky Way and the vast dark matter halo surrounding the galaxy are not two objects. They are two regions of the same continuous structure, a single distribution of fermionic dark matter, concentrated to extreme density at the center, then tapering outward through the galaxy, eventually becoming the diffuse halo that observations have long required to be there. The core and the halo are one. To appreciate why this matters, it helps to recall how dark matter was first inferred. In the 1930s, Fritz Zwicky was observing galaxies in the Coma cluster and noticed that they were moving far too fast. The visible mass, all the stars, all the gas, could not generate enough gravity to hold them together at those speeds. Something unseen was adding mass to the system. He called it dark matter, and the term stuck. Decades later, the same problem appeared at smaller scales. Stars in the outer regions of individual galaxies were orbiting too quickly. The visible matter at the center could not account for the velocities measured at the edges. Dark matter had to be present, distributed through and around the galaxy, providing the extra gravitational pull that kept the rotation curves from falling off. These observations are among the most replicated in modern astronomy. The effect is real. Something is there. It cannot be seen, cannot be detected directly, and has so far resisted every attempt to identify it in a laboratory. The fermionic dark matter model makes a specific prediction about how this invisible mass is distributed. And that prediction recently encountered a piece of observational evidence it was not designed for. In 2022, the European Space Agency's Gaia mission released a detailed map of stellar motions across the Milky Way. Gaia is tracking the positions and velocities of close to 1 billion stars, building a picture of galactic dynamics more precise than anything previously attempted. When astronomers analyzed the outer edges of the galaxy in that dataset, they found something unexpected. The rotation curve drops off. In the outermost arms of the Milky Way, stars are moving more slowly than most dark matter models predict. This is called Keplerian decline, and it had not been clearly observed in our galaxy before. Most standard dark matter distributions, smooth, extended halos without sharp boundaries, struggle to reproduce it. The outer stars should be moving faster if the dark matter extends indefinitely outward in a diffuse cloud. But fermionic dark matter, governed by the Pauli exclusion principle, would form a halo with a defined edge. The quantum pressure that prevents the core from collapsing into a singularity also governs how the halo spreads. It does not trail off smoothly into infinity. It has a boundary. Beyond that boundary, the gravitational influence drops, and stellar velocities fall accordingly. The Gaia observation fits. Not perfectly. No model fits every observation perfectly, and the researchers are careful to say so. But the fermionic dark matter halo naturally produces a structure consistent with what Gaia recorded, without requiring additional adjustments to force the match. This is the quality that makes the proposal difficult to set aside. It was not constructed to explain the Gaia data. It was constructed to explain the orbital behavior of stars near Sagittarius A. The Gaia result arrived independently, and the model accommodated it. One proposal, two problems. The same structure at two entirely different scales. That kind of reach is rare in physics. Most hypotheses are narrow. They are built to explain a specific observation, and they succeed or fail on that single test. A theory that simultaneously accounts for the behavior of a star completing its orbit in 16 years, and the rotation speed of stars tens of thousands of light years from the galactic center, is doing something more than patching a local problem. It is describing something about how the galaxy is built. Whether that description is correct is a separate question. But the geometry of the proposal, the single unified structure, dense at the center and diffuse at the edges, is not arbitrary. It follows from the physics of the particle being proposed. The behavior of dark fermions under gravity and quantum pressure produces this shape naturally, without being tuned to match a predetermined answer. That is what the La Plata team means when they call it elegant. And it is why, despite the consensus, the question has not quietly gone away. There is one more piece of evidence that any serious alternative to the black hole model must confront: the image. When the Event Horizon Telescope collaboration released a picture of Sagittarius A in 2022, the coverage was nearly universal. A glowing ring of superheated gas, warped into a near-perfect circle by the gravitational field of whatever sits at the center. A dark region inside that ring where no light escapes. It was described repeatedly and across every major outlet, as a photograph of a black hole. The description is understandable. The image is striking. But the language is imprecise in a way that turns out to be important. What the Event Horizon Telescope captured is thermal radiation from gas falling inward, bent into a ring by extreme gravity surrounding a region from which no photons reach the detector. The darkness at the center is real. The ring is real. What produced them, the specific nature of the object responsible, is what the image cannot directly confirm. The 2024 paper from Arguelles and collaborators at La Plata ran the calculation. A fermionic dark matter core of sufficient density would bend light with nearly the same force as a black hole of equivalent mass. The photons traveling near it would follow curved paths. Gas falling toward it would heat and radiate. The resulting image, viewed from Earth, would show a bright ring surrounding a dark center. The shadow would appear even without an event horizon. This is not a claim that the EHT image is consistent with anything. Most objects do not produce this effect. The dark matter core must be extraordinarily dense. The model requires it for the gravitational lensing to reach the necessary magnitude. But under those conditions, which the fermionic dark matter model predicts for Sagittarius A, the image produced would be, within current instrumental resolution, indistinguishable from the black hole scenario. The ring we see is not proof of a singularity. It is proof of extreme gravity. The source of that gravity remains the question. There is, however, a signature that would distinguish the two. Around a true black hole, the geometry near the event horizon does something specific to light. Photons that pass close enough do not simply curve and escape. They can be captured into unstable orbits, spiraling around the black hole multiple times before either falling inward or escaping outward. This phenomenon produces what are called photon rings, nested bright structures layered inside the main emission ring, each successive ring representing that had completed additional loops before escaping. A dark matter core cannot produce photon rings. Without an event horizon, there is no region where light is trapped into those looping paths. Photons are bent by the core's gravity, sometimes severely, but they escape. The nested ring structure does not form. If the next generation of instruments could resolve photon rings around Sagittarius A, the black hole model would gain a distinction the dark matter alternative cannot replicate. That resolution is being worked toward. NASA's Black Hole Explorer mission is in development, a space-based radio telescope designed to link with an upgraded Earth-based array, creating a virtual instrument larger than the planet. The angular resolution required to image photon rings around Sagittarius A is extreme, and the timeline is measured in decades rather than years. But the target is defined. The measurement is possible in principle, and eventually in practice. In the meantime, a different instrument is already gathering relevant data. The Gravity Interferometer, operating at the Very Large Telescope Interferometer in Chile, is tracking the orbital precession of S2 with extraordinary precision. As S2 completes each loop around Sagittarius A, the orientation of its orbit shifts slightly, a relativistic effect predicted by general relativity, analogous to the precession measured in Mercury's orbit around the Sun. The direction of that shift and its exact magnitude depend on the mass distribution of the central object. For a black hole, the precession follows a specific pattern. For a dark matter core, the pattern differs subtly because the mass is not perfectly concentrated at a point, but distributed across a dense sphere. The difference is small, but gravity is approaching the precision required to detect it. Future measurements of S2's orbital evolution provide the first genuine discriminating constraint between the two models. At the opposite end of the experimental scale, direct detection experiments are beginning to search for dark fermions themselves. The NEON experiment in South Korea is looking for the faint energy signatures. that would result from a dark matter particle colliding with an electron. An event so rare that even a single confirmed detection would be extraordinary. If dark fermions interact only gravitationally, as the model proposes, neon may not find them. But if the particle properties allow even marginal, non-gravitational interaction, a signal might eventually surface. The search is active. The constraints are tightening, slowly, from multiple directions at once. What is notable about the situation is that the fermionic dark matter model is not simply untestable speculation. It makes specific predictions about orbital precession, about the absence of photon rings, about the shape of the galactic rotation curve that future instruments can evaluate. The model could be confirmed. It could be ruled out. The path toward a definitive answer exists, even if the journey along it is measured in years and decades. That is what distinguishes a serious scientific hypothesis from an interesting story. This one has both. There is a detail buried in the James Webb Space Telescope data that the fermionic dark matter model was not built to explain. And yet it explains it. Since Webb began returning data from the early universe, astronomers have been puzzling over a class of objects appearing in the centers of extremely distant galaxies. Galaxies so far away that their light has been traveling for more than 13 billion years before reaching the detector. These objects are compact, intensely bright at certain wavelengths, and appear to be extraordinarily massive. Hundreds of millions of solar masses, in some cases, billions. They have been given an informal name, little red dots. The problem is not that they exist. The problem is when they exist. The galaxies hosting these objects are being observed less than 1 billion years after the Big Bang. In cosmological terms, that is early, extremely early. The universe at that stage was young enough that the structures astronomers currently understand, the slow accumulation of gas, the formation of stars, the collapse of stellar remnants into black holes, the gradual growth of those black holes through feeding and merging across billions of years, had simply not had time to run. There is no established pathway that produces a black hole of hundreds of millions of solar masses within the first billion years of cosmic history. The mechanisms exist in outline: rapid accretion, direct collapse, seeding from massive early stars. But each pathway carries constraints, and when those constraints are applied to the objects Webb is finding, the timelines become extremely difficult to reconcile. Something that massive should not be there yet. Fermionic dark matter does not share that constraint. In the dense, hot conditions of the early universe, dark fermions would have been present from the beginning, not as a product of stellar evolution, not as a remnant of collapse, but as a fundamental component of the matter content of the cosmos. Under sufficient gravitational pressure, they would begin to gather. The Pauli exclusion principle would prevent full collapse, but it would not prevent concentration. Dense cores could form in the early universe, without stars as a starting point, without needing billions of years of hierarchical growth. The timeline that makes supermassive black holes implausibly early is not a problem for fermionic dark matter cores. They can be established sooner because their formation pathway does not depend on prior stellar generations. This does not prove the little red dots are dark matter cores. Several competing explanations exist for these objects, and the debate within the astronomy community is active and unresolved. Researchers propose they are heavily obscured quasars. Others suggest the estimates from current observations may carry systematic errors that make the objects appear more massive than they are. The discussion is ongoing, and no consensus has formed. But the fermionic dark matter model fits the morphology, the mass range, and the timeline without being adjusted to do so. A model built to place a stellar 16 is making predictions consistent with objects observed 13 billion light-years away. That kind of explanatory reach accumulates weight, even when no single piece of it is definitive. It is worth pausing here to stock of what has actually been established and what has not. The fermionic dark matter model has been shown to reproduce the orbital behavior of S2 and 5G objects around Sagittarius A, with less than 4% deviation from the black hole model. It produces a galactic rotation curve consistent with the Gaia observations of Keplerian decline at the outer edges of the Milky Way. It generates a central shadow in simulated imaging consistent with the Event Horizon Telescope result. It accommodates the apparent masses and formation timescales of compact objects in the early universe detected by Webb. None of this proves the model is correct. The black hole interpretation of Sagittarius A remains the consensus position of the astronomical community, and the researchers at La Plata have been explicit about this. Their work does not demonstrate that the black hole model is wrong. It demonstrates that a fermionic dark matter model cannot be ruled out by current data. Those are very different claims, and the distinction matters. Science does not advance by replacing one certainty with another. It advances by identifying where certainty is not yet earned, and then building the instruments, running the observations, and doing the calculations required to earn it. What Crespi, Arguelles, and their collaborators have done is establish that a question previously considered settled is not in fact settled. The object at the center of the Milky Way has been measured with extraordinary precision. Its gravitational influence is among the best characterized in astronomy. But its nature, what it actually is, what is happening at its center, whether it has an interior at all, remains beyond the reach of current observation. The evidence fits two models. That is not a failure of science. That is science functioning correctly, accumulating precision, until the precision becomes sufficient to choose. The choosing has not yet happened. Consider what it would mean if the model is correct. Not the technical consequences, not the adjustment to textbooks or the revision of cosmological simulations. The deeper implication, the one that sits underneath the physics and refuses to stay quiet. For decades, two of the most fundamental mysteries in modern science have been treated as unrelated problems, separate departments, separate conferences, separate careers spent on each. The first mystery: what is the object at the center of our galaxy? The second mystery: what is dark matter? The first is a question about a single point in space, 27,000 light-years away smaller, across than the orbit of Venus. The second is a question about 85% of all the matter that exists, the invisible scaffolding that determines the large-scale structure of the entire universe, the reason galaxies hold together, the reason the cosmic web has the shape it has. One question is local, one question is total. The La Plata proposal says they are the same question. The dense core at the center of the Milky Way and the vast halo stretching beyond the visible galaxy are not two structures that happen to coexist. They are two expressions of the same particle, the same distribution, the same physics out across scales that differ by a factor of billions. What sits at the galactic center is not a singularity surrounded by unrelated dark matter. It is the innermost concentration of a single continuous object that effectively is the galaxy, from its deepest core to its outermost boundary. If that is true, the history of the question changes. Astronomers have spent nearly a century searching for dark matter, building detectors deep underground, analyzing gamma-ray telescopes for annihilation signals, running collider experiments, looking for particles that leave no trace. All of that searching has assumed dark matter is something to be found out there, separate from the objects already known, hiding in a sector of physics not yet mapped. But if dark fermions are real, they do not produce annihilation signals. They do not show up in colliders. They interact with ordinary matter only through gravity, which means every detector built on different assumptions has been looking in the wrong place using the wrong logic. The absence of a signal would not be a failure of dark matter to exist. It would be a consequence of its nature. And the object astronomers have been studying for decades, the one generating the orbital paths of the S-stars, the one whose shadow appears in the Event Horizon Telescope image, the one whose mass won a No prize to measure. That object would not be a black hole. It would be the largest directly observable concentration of dark matter in the known universe, sitting at the center of our own galaxy, measured to 4 significant figures, imaged in radio wavelengths, studied continuously for 30 years, not hidden, not hypothetical, already found, and simply misidentified. That possibility will either be confirmed or eliminated by instruments that do not yet exist, using measurements that have not yet been made. The photon ring observation, the orbital precession data from gravity. The direct detection results from experience like neon. Each of these carries the potential to close one branch of the question, and none of them will deliver a verdict quickly. In the meantime, the object continues its work regardless of what we call it. The S-stars complete their orbits. The gas clouds distort and recover as they pass through the intense gravitational field at the galactic center. The halo, if it exists as the model describes, continues to shape the rotation of every star in the Milky Way, including the Sun, including the entire local neighborhood of stars, at this moment, without interruption. What is sitting at the center of the galaxy has been there for billions of years before the first radio signal from it reached a detector on Earth. It will be there long after any conclusion is reached about its nature. The uncertainty is ours. The object does not share it. There is something in that asymmetry worth holding for a moment. We have built telescopes that can track the orbit of a single star moving at 8% the speed of light 27,000 light-years away. We have linked radio dishes across the diameter of Earth to capture the shadow of a region smaller than our solar system. We have launched a space telescope that can image galaxies formed less than 1 billion years after the universe began. And at the end of all that precision, the most fundamental question about the object at the center of our own galaxy remains open. Not because we have not looked carefully enough, because what is there, our existing categories were not built to contain. The history of astronomy is, in part, a history of misidentification. The first radio signal from the direction of Sagittarius A was detected in the 1930s by Carl Jansky. At the time, no one knew what it was. Black holes were considered mathematical curiosities, objects that fell out of Einstein's equations, but were not taken seriously as physical realities. The signal was attributed to clouds, to star clusters, to supernova remnants. The correct interpretation was not available yet, because the conceptual framework required to hold it had not been built. It took 4 decades before the object was identified as a single compact mass. Another 2 decades before the orbital data of the surrounding stars made a supermassive black hole the dominant interpretation. Another decade before the Nobel Prize was awarded for measuring it. And in 2026, a paper published in a peer-reviewed journal demonstrates that the measurements which earned that prize are also consistent with something else entirely. This is not a story about science failing. It is a story about how science actually works, not as a straight line, from ignorance to certainty, but as an iterative narrowing, where each generation of instruments closes some questions and opens others, where consensus forms around the best available explanation until a better one arrives, with sufficient evidence to displace it. The black hole interpretation of Sagittarius A is not wrong, because the fermionic dark matter model fits the data. It remains the consensus, because it has accumulated the most explanatory support across the broadest range of observations, and because black holes of stellar origin are directly observed. Their formation physics is understood, and scaling that physics upward, however imperfectly understood, is a more conservative move than invoking a new class of fundamental particle not yet detected by any instrument. Science is conservative by design. It should be. The history of physics is littered with elegant proposals that explained existing data and were later ruled out by new data. Elegance is not evidence. Consistency is not confirmation. A model that fits current observations has cleared a minimum threshold, not a final one. What the La Plata team has done is clear that threshold. What remains is everything after it, and what comes after is a period of observation that will last, by any realistic estimate, at least a generation. The Black Hole Explorer mission is in early development. The Next Generation Event Horizon Telescope is being planned. The Gravity Interferometer will continue accumulating orbital data on S2 for years. Direct detection experiments will run and either find something or constrain the parameter space further. During all of that time, the question will remain open. Not dramatically open, not in the way that suggests science is lost or confused, but open in the precise technical sense that the available data does not yet compel a single answer. 2 models, 1 dataset, insufficient resolution to choose. There is a version of this story that ends with confirmation of the black hole. The photon rings appear in future imaging. The orbital precession of S2 matches the point mass prediction. No dark fermion signal surfaces in any detector. The consensus tightens into certainty, and the fermionic dark matter hypothesis is archived alongside the other proposals that fit the data of their era and were eventually superseded. There is another version where the precession data from gravity diverges from the black hole prediction in a way that a distributed dark matter core explains, where Webb continues finding compact massive objects in the early universe that black hole formation models cannot accommodate, where the fermionic dark matter halo becomes the only structure that fits the full range of galactic observations simultaneously. Both versions are currently permitted by the evidence, that is, the actual state of knowledge about the center of our own galaxy is in 2026, not ignorance. The measurements are extraordinary in their precision. But precision and completeness are different properties, and the data set is not yet complete enough to close the question. The object at the center of the Milky Way has been observed, measured, imaged, and studied continuously for nearly half a century. Astronomers know its mass to 4 significant figures. They know the orbital parameters of the nearest stars around it with a precision that would have seemed impossible a generation ago. They have an image of the light bending around it, and they still do not know what it is. That is not a gap in the data waiting to be filled by the next instrument. It is a structural feature of the current moment in physics, a point where 2 competing frameworks both satisfy the available evidence, where the measurement required to distinguish them lies just beyond current capability, and where the answer, when it comes, will not simply update an entry in an astronomy database. It will change what the galaxy means, because if the object at the center is a dark matter core, if the halo and the core are one continuous structure, then the Milky Way is not a collection of stars orbiting a black hole embedded in a cloud of unknown particles. It is something more unified than that, a vast distribution of dark matter, shaped by quantum pressure into a sphere with a defined boundary, concentrated to extreme density at the center, diffuse at the edges, and continuous throughout. Every star in the galaxy, including the Sun, would be moving through dark matter. Not past it, through it, embedded in it, part of a single gravitational structure that extends from the object at the galactic center to a boundary tens of thousands of light years beyond the outermost stars. The galaxy, in that picture, is not a disk of stars floating in a halo. The halo is the galaxy, and what sits at its center has been there the entire time, not as an absence, not as a region of no return, but as the densest part of the structure that everything else belongs to? That question is still open. The instruments that will close it are still being built, and the object itself continues, indifferent to the uncertainty, bending stars around it at 8% the speed of light, 27,000 light-years from here, at the center of everything we have ever called home. There is a particular kind of discomfort that comes from realizing a question you thought was answered is not. Not the discomfort of ignorance, that is familiar, expected, manageable. The discomfort of false certainty. The feeling that the ground underfoot, which seemed solid, is something more provisional than it appeared. Most people who know anything about the center of the Milky Way know the same thing. There is a supermassive black hole there. They may have seen the image. They may have read about the Nobel Prize. The fact has the texture of settled knowledge, the kind of thing that belongs in the same category as the age of the universe or the structure of DNA. A hard fact. A closed question. It is not a closed question, and the implications of that openness extend further than Sagittarius A. Dark matter is not a peripheral problem in physics. It is not a small correction to an otherwise complete picture. It is a gap at the center of the standard model of cosmology. A placeholder for 85% of all matter that exists, matter whose nature remains entirely unknown after nearly a century of searching. Everything astronomers know about how galaxies form, how the cosmic web is structured, how the large-scale architecture of the universe evolved from the conditions after the Big Bang, all of it depends on dark matter, behaving in ways consistent with the models, even though no one knows what dark matter is. That is an extraordinary situation. The most successful cosmological framework ever developed rests on a foundation that is, at its core, unidentified. Fermionic dark matter is one proposal for what that foundation is made of. It is not the only proposal, and it may not be the correct one, but it is notable for what it connects. It does not add a new particle to explain a local anomaly. It proposes a particle whose behavior, governed by quantum mechanical principles already understood, naturally produces a structure that fits observations at scales ranging from a 16 years to the rotation of the outer galaxy, measured by a satellite tracking a billion stars. The particle is speculative. The connections it makes are not arbitrary. What the La Plata researchers have placed on the table is a question with a specific shape. Is it possible that the two deepest unsolved problems in modern astrophysics, the nature of Sagittarius A and the nature of dark matter, are not two problems at all? Most of the history of physics consists of moments where things that appeared separate turned out to be the same thing. Electricity and magnetism, space and time, energy and mass. The pattern is consistent enough that when a proposal appears claiming two apparently unrelated phenomena share a common origin, the claim deserves serious evaluation rather than immediate dismissal. This one is receiving serious evaluation. The paper cleared peer review. The researchers are continuing to develop predictions that future instruments can test. The model is not resting on its initial result. It is being extended, challenged, and refined. That is the correct process, and it is ongoing. What it leaves behind for anyone paying attention is a specific kind of uncertainty. Not the vague uncertainty of a mystery too large to approach, but the precise uncertainty of a question that has been narrowed to where the answer is visible in outline, waiting for an instrument sharp enough to resolve it. The photon rings are either there or they are not. The orbital precession of S2 will either match the point mass prediction or it will not. The dark matter halo will either have a defined boundary consistent with a fermionic structure or it will not. The universe is not withholding the answer. The answer is already there, encoded in the geometry of light, bending around an object 27,000 light-years away, in the subtle drift of a stellar orbit, in the rotation speed of stars, at the outermost edges of the galaxy. The only thing missing is the resolution to read it. And while that resolution is being built, while the next generation of telescopes is being designed and launched and calibrated, the object at the center of the Milky Way continues doing what it has always done, holding everything together, bending stars into orbits so tight and so fast that measuring them required the better part of a human lifetime of observations, generating a shadow that appears in radio wavelengths from 27,000 light-years away as a ring of light surrounding a central darkness. Black hole or dark matter core. The gravity is real. The orbits are real. The shadow is real. What produced them is the question that remains. And perhaps that is the more honest picture of where science actually stands. Not at the edge of complete knowledge, looking back over settled ground, but somewhere in the middle of a longer story, surrounded by measurements precise enough to be humbling and gaps large enough to matter. The center of the galaxy is not a solved problem dressed in impressive numbers. It is an open question wearing the costume of a settled one. And the difference between those two things is everything.